Welcome to your deep dive. If you're looking for a shortcut to understanding, well, some really cutting-edge cosmology, you're in the right place. Today, we're tackling dark matter. It's one of the biggest puzzles out there. This totally invisible stuff, it doesn't emit light, but its gravity basically sculpts the entire universe. The structure, the shape, even how galaxies move. It's the universe's silent architect.
That's a great way to put it. Silent, unseen, but incredibly powerful. And that's where this really innovative project comes in, COZMIC. It stands for Cosmological Zoom-In Simulations with Initial Conditions Beyond Cold Dark Matter. Quite a mouthful.
Yeah, it is. So what's the core idea?
Well, they're essentially testing different laws of physics. They create these virtual clones of our own Milky Way galaxy on supercomputers.
Virtual Milky Ways. Okay.
Exactly. And they tweak the physics in each clone to see which one ends up looking most like the real thing. It's a new way to get at this dark matter problem.
Interesting. So think of this deep dive as your direct line into that cutting-edge research. We're trying to unlock some pretty big secrets here. Maybe let's start at the beginning, though. Dark matter feels like, common knowledge now in cosmology, but how did scientists even figure out it was there? It's invisible.
Right, it wasn't obvious at all. It goes back to the early 20th century, actually. Astronomers started noticing things moving. Strangely. Stars, whole galaxies just weren't behaving the way they should if only the visible stuff, stars, gas, dust, was providing the gravity. The math didn't add up.
Okay, so anomalies in movement. And wasn't it Fritz Zwicky who actually coined the term?
Yes, exactly. Zwicky, back in the 1930s, he was looking at the Coma Cluster, a huge group of galaxies, and he calculated that they were moving incredibly fast. So fast, based on the light they emitted, they should have just flown apart, but they weren't. So he proposed there must be some unseen mass, some dunkel materia, dark matter, holding it all together gravitationally.
Dunkel materia, okay. But his idea didn't catch on immediately, did it?
Not widely, no. It took several decades. Then came Vera Rubin's work in the 1970s. That was really crucial. She studied galaxy rotation curves. Basically, how fast stars orbit the center of their galaxy at different distances.
Right, and she found something weird there, too.
Totally weird. According to standard gravity based on visible matter, stars further out should orbit much slower, like planets in our solar system, right? Mercury zips around, Neptune crawls. But Rubin found stars way out in the galactic fringes were orbiting just as fast, sometimes even faster, than stars closer in. Flat rotation curves, they call them.
Which means?
Which means there had to be a huge amount of unseen mass extending far out beyond the visible light of the galaxy, a massive halo of something else. Her work really provided compelling evidence that this invisible dark matter wasn't just some quirk in galaxy clusters. It dominated the dynamics of individual galaxies, too. Way more dark matter than normal matter.
So we know it's there from gravity. But here's the kicker, right? Decades later, after tons of effort, we still haven't directly detected it. It doesn't give off light, doesn't seem to reflect it. It's like a ghost. How do you even confirm what it is if you can't, grab a piece of it?
That is the million-dollar question, or maybe trillion-dollar question, given the scale. And that's precisely why COZMIC is so important. It's led by cosmologist Maria Glusevich and astronomer Ethan Nadler, and their whole approach is about simulating possibilities. If we can't catch it directly, let's see if we can figure out its properties by how it should affect things.
Okay, so back to these virtual Milky Ways. They build these replicas using supercomputers, advanced algorithms, but they're not just making identical copies, are they?
No, that's the key. They take the initial conditions like the state of the universe shortly after the Big Bang that would lead to a galaxy like ours, but then they change the rules for dark matter within the simulation.
Change the rules? Like how?
Well, they can play with things like, what if dark matter particles have a certain mass? What if they interact with each other? What if they interact with normal matter, like protons and electrons, in some way? These are fundamental parameters they can tweak.
So it lets them ask questions we couldn't really test before.
Exactly. They can simulate what a Milky Way would look like if dark matter behaved according to Theory A versus Theory B versus Theory C. They can model its quantum properties, maybe, or how it clumps together. And then this is crucial. They compare the results. They look at their simulated galaxies and ask, does this look like the actual Milky Way we observe with telescopes?
Ah, okay. So it's like creating a lineup of suspects. Each simulation is a different theory of dark matter, and they're trying to see which one matches the crime scene, our actual galaxy.
That's a perfect analogy. It's forensic cosmology using supercomputers. They blend these precise initial conditions with novel physics ideas to peek into this unseen realm.
Let's get into some of the suspects then. What are some of the alternative physics they're testing? You mentioned a billiard ball model. Sounds fun.
It does, yeah. So in this scenario, imagine dark matter particles aren't totally aloof. Imagine back in the very early universe, when things were incredibly hot and dense. What if every dark matter particle frequently collided with protons? Literally like tiny billiard balls knocking against each other.
Okay, constant collisions early on. What would that do in the simulation? What cosmic problem is that trying to solve?
Well, one long-standing puzzle is the missing satellites problem. Standard theories, usually called cold dark matter or CDM, predict our Milky Way should be surrounded by many, many more small dwarf galaxies, these little satellite galaxies, than we actually see.
Right, there's a discrepancy there.
There is. So the KOZ-EMA simulations test this. If dark matter particles did collide frequently with protons early on, that interaction, that friction, could have effectively smoothed things out. It could have prevented the smallest clumps of dark matter from collapsing and forming those tiny galaxies. So in the simulation, these collisions essentially erase the predicted excess small satellites.
Interesting. So it could potentially explain why we see fewer dwarf galaxies than simple CDM expects.
Potentially, yes. And it would also change the speeds of the dark matter particles left in the halo today. So KOZ-Milky lets them calculate, okay, if this happened, what specific velocity signature should we look for in the stars or gas orbiting our actual Milky Way? It gives observers something concrete to hunt for.
Okay, so that's one possibility. What about dark matter interacting directly with normal matter, baryonic matter today? You said that's different from standard cold dark matter ideas.
It is quite different. The standard CDM model basically assumes dark matter particles just goes right through normal matter. Maybe a very occasional, incredibly rare interaction, but mostly they ignore each other. But KOZ-Milky tests variations where that's not true. Maybe some dark matter particles do scatter off protons or electrons more often. Imagine some particles sailing through, others bouncing off.
Okay, and what would the consequences of that be?
Well, that's what they're exploring. Could it affect how stars form? Maybe it changes the way gas behaves and cools within a galaxy. Could it even leave a subtle imprint on the cosmic microwave background, that sort of baby picture of the universe? The simulations let them model these effects and see if they produce signals we might actually find in telescope data, signals we might have previously missed or misinterpreted.
So it opens up new ways to look at existing data, potentially.
Exactly.
And there was a third one you mentioned, self-interacting dark matter, so dark matter bumping into itself.
Yeah, SIDM, self-interacting dark matter.
Right.
In this picture, dark matter particles might ignore normal matter, mostly, but they collide with each other fairly often over cosmic history.
What does that do to a galaxy's structure?
It can significantly reshape the distribution of dark matter, especially in the dense central regions of galaxies. See, standard cold dark matter predicts very sharp density peaks, cusps, right at the center of galactic halos. But observations of some galaxies, especially smaller ones, often show flatter, smoother cores instead of cusps.
Ah, another discrepancy between theory and observation.
Right, and self-interactions could solve this. If dark matter particles collide, they effectively transfer energy. It's like kinetic energy exchange. This can smooth out the central density peak, turning a predicted cusp into an observed core. It also affects how galaxies assemble over time, how their halos are built up. So again, this simulations test. If dark matter interacts with itself this much, what specific structural features should we see in galaxies like the Milky Way?
It really sounds like they're turning these theoretical ideas into concrete, testable predictions about what our galaxy should look like. Which brings us to the crucial step, comparing simulations to reality. How exactly do they bridge that gap?
It's a very detailed process. They essentially take the output of their simulations, the predicted positions and velocities of stars, the distribution of gas, the number and location of satellite galaxies, and they project it onto the sky as if we were observing it. Then they compare that synthetic data directly with real astronomical surveys, maps of stars from Gaia, gas maps from radio telescopes, counts of dwarf galaxies from deep sky surveys.
And they're looking for the best match.
They're looking for the best match. Which simulated universe, with its specific dark matter physics, produces a Milky Way clone that looks most like our Milky Way? It's pattern matching on a cosmic scale.
It's like trying on different pairs of glasses to see which one brings the universe into focus. And we've got some powerful new eyes coming online, right? JWST, the Rubin Observatory, Euclid.
Absolutely critical. These next-generation telescopes will provide unprecedented data quality and quantity. JWST is already peering deeper than ever. The Rubin Observatory will map the southern sky over and over, creating this incredibly detailed dynamic map. Euclid is designed specifically to map the geometry of the dark universe. All this new data will provide much sharper tests for the QOZ basic simulations. It will help us distinguish between these different dark matter scenarios much more effectively.
So QOZ isn't just a one-off project. It's going to keep evolving as the data gets better.
Definitely. The researchers plan to expand the range of physics. They test the parameter space. They'll incorporate more complex physics about how galaxies themselves form and evolve, feedback from supernovae, black holes, and they're even starting to use machine learning to help sift through the massive amounts of simulation data and observational data to find those subtle patterns that might reveal dark matter's true nature.
Wow. It sounds like an incredibly dynamic field right now. All these efforts, the simulations, the new observations, they're all converging on these huge questions.
They really are. What is dark matter made of? Is it one particle? Multiple. How does it actually talk to the rest of the universe, the stuff we can see? And how did this interaction shape everything from the smallest dwarf galaxy to the largest cosmic structures?
We're basically using these virtual universes, these Milky simulations, to sift through all the possibilities, trying to find the version of reality that finally clicks, the one that matches what we see out there.
That's the hope.
Hmm.
Find the simulation that mirrors our reality, and you might just unlock the secret of dark matter.
So the final thought for you, the listener, is this. Which of these simulated realities holds the key? Could it be the billiard balls, the self-interactions, something else entirely? Are we genuinely getting close to figuring out this massive cosmic mystery? And just imagine the implications. Understanding dark matter wouldn't just solve one puzzle, it would rewrite our understanding of the entire cosmos. Something to really think about.